we went through the linear quantizer, and we went through some math, and we developed signal to quantization noise ratio equation. And what we saw there is that the signal to quantization noise ratio depends on the PDF of the signal. And as the PDF of the signal becomes more and more spiky, or that is non-uniform, you actually start having some hits in your signal to noise ratio. We saw that with the uniform signal, you get essentially 20 log of Q, where Q is the number of quantization levels. But then if your signal is non-uniform, you may end up with a penalty. And then particularly bad are those signals that are focused around the origin. And what happens is we kind of are unlucky there, is the signals that we care about, let's say voice and music, they spend a lot of time around zero. They're actually in this area where if you present them to the uniform quantizer, you end up having a signal to quantization noise ratio penalty. It is lower than 6 times n, where n is the number of bits that you use for the quantizer. So the solution to that is to use a non-uniform quantizer, to essentially have your quantization levels depend on a PDF of your signal. And in the portion of the magnitudes where your signal dwells the most, have a finer quantization, and in the portion of the signal magnitudes where probability of signal being there is less, you have coarser quantization. What that boils down practically is we usually typically quantize much finer at close to the zero, and then your quantization steps grow away from the zero. But that doesn't have to be the case. As you will see, we will cover this in general, and devise the equation in general, and then you will be able, based on whatever is the particular signal that you're dealing with, devise a non-uniform quantizer. Now, when it comes to non-uniform quantizer and just the story that I just said, well, it seems like it's complex, right? Because now I have to design quantizer that depends on a probability density of your signal, right? And every signal is different, so that means I would have to have a lot of different designs to accommodate for that. And the way how we deal with that is we actually leave the quantizer alone and make it uniform as we presented the last time, and then we pre-process our signal before presenting it to the quantizer. And we pre-process the signal, then perform the quantization, and then at the end, when we want to reconstruct the signal, we have to undo what we did through the process. So let me do some drawing, and then we're going to wrap up some math. So here's where I'm going to start. I'm going to start here by uniform quantizer. So this is your input, and this is your output. And we have our steps that look exactly the same as the last time. These deltas are the same. The quantization step has the same delta all across the board. So this is, again, delta and so on. So these are steps. So this is a uniform quantizer, uniform. But before we present the signal to this quantizer, we're going to introduce a nonlinear amplifier that I'm going to call compressor. And the characteristics of the compressor is going to be somewhat like this. So this is going to be your input, and this is going to be your output. And this is going to be your FMX, right? Your curve of the compressor. Now, sorry about this. Let me move this. That's the consequence of staying, when you're writing on a board, you're practically part of the board. So your vision is this. So this needs to align, right? So here's your out. This is in. So how is this making your quantization step non-uniform? This is where you're going to feed your input, your signal. Now let's look at what happens to these ranges as I project them through this compressor. So this is the first quantization range, right? Anything that falls within this interval will end up being quantized as this value. Now, these intervals are uniform in length when it comes to the quantizer. But let's look at what happens when you project them through the compressor. The first interval is this large, right? So what is the first interval? From here to here, right? Because this small interval now is going to be mapped into this quantization level. If you look at the second one, look how large is the second interval. It's slightly larger, right? And then everything that falls within this interval is going to be quantized as a third level. So you can see now from the input standpoint, these quantization steps grow, right? They are very fine in this area, and they become progressively larger as you move to the higher amplitudes. So there are more, the quantization is finer here and coarser towards the end, right? So this, let's call this level here xi plus 1, and this is your input that comes into this. So this amplifier we're going to call compressor. Now, let's once you go through quantization and then you, let's say, feed this into a communication system and so on, and you recover your quantization signal levels, then you have to actually do inverse mapping. So this is output, and this is an input for this one, and you're going to have a curve that is an inverse, I'm going to say f minus 1 of x, that is an inverse of this curve here. You see, just to see that it's inverse, look at this one is kind of close to the out, and this one is close to the in, right? So they're going to, net product of these two is going to be equal to 1, right? They're going to cancel each other. So if I look at, for example, let's just trace, let's say this is your input. Let me call this just simply x. This x is going to be mapped through this into this value here for the quantizer. The quantizer is going to assign this value to it. So this is going to be x cubed. And then this x cubed is going to travel through your system. And then through expander, it's going to be out, which I'm going to call 1. All right, so here's how it goes. You go through here, through your compressor, to this value here. Then this value gets quantized, and then it travels, and then it gets mapped into this. Okay? So that's how the single sample travels. This is, as I said, called expander. And essentially the function of this one is an inverse of the function of this guy here. Now, what is our goal here today? Our goal is to describe this mathematically, and to kind of derive the expression for signal to quantization noise ratio that is now going to be function of principally three things. Your delta, which is the quantization step of your uniform quantizer, is going to be function of the PDF of your signal, which is this. We discovered that it has to be function last time, and then the third, it's going to be function of this f of x, and we're going to try to select f of x in such a manner to minimize the effect of the PDF of the signal, to eliminate the effect of the PDF of the signal. Now, before a lot of times, when it comes to math, all the trees obscure, you know, the forest. So before we go into that, let me explain how it works practically. If you have a signal that dwells a lot about the origin, and just like in this case, let's say my signal is here. What does this compressor do? It will actually take this range here and essentially spread it over larger range of magnitudes, right? It will take this, let's say these two intervals here, where the signal is going to be most of the time, now occupy much larger interval, you know, before it's presented to the quantizer. So it's taking the low values and it's amplifying them so that it modifies the PDF. So the signal is now not focused only about the origin, but has a PDF that is distributed across larger range of values. Okay, and then it quantizes that, and then on the back, you know, to bring the signal back to what it was, it needs to shrink it to the same range that it was when it came in here. Go ahead.
Why do we need a compressor here? To quantize that?
I just explained to change
like
the PDF of your input signal. Your input signal has a PDF which says that it's mostly around the origin. When you have a compressor, it takes that range around the origin and makes it much broader. So
you just only have the amplitude that you want to play around with the amplitude and minimize the PDF. So that's why you have the compressor.
It changes the PDF. It changes the shape of your PDF. If you have a signal, let me just kind of say, let's say this is the PDF of your signal. And let's say it looks like this, right? So this is typically how so this is PDF of the signal. Then, after compressor, it might look somewhat like this. Right? So what does this do? It takes all of these, the signal is dwelling around the origin, but because it's amplifying, it's stretching this origin into much larger interval here, it actually modifies the PDF. Now, if you look at this, this is much closer to the uniform distribution, and therefore it's more appropriate for a uniform quantizer, right? I have a music.
Why is it called a compressor when it's actually expanding the?
I was thinking about it too. I don't know.
Yeah,
we're going to really expand. Why?
Yeah, but because that's how I know why is it called, and this goes back to Andy's question. You know, is that like when you press compressor on your guitar? Right?
Yes, because.
Okay, so let me explain what is being compressed, right?
I know.
What is being compressed is the dynamic range,
yes.
right? Let's just plot the signal in that is uncompressed. Uncompressed signal looks like this, right?
Right.
So if you look at the power, there is this is a maximum power and this is a minimum power, and the dynamic range of the power is very large, right? There are portions where it's really quiet and the portions that is relatively loud. What the compressor does, it takes these portions that are really quiet and then amplifies them, right? So you end up with something that looks like this. In the portions where it's quiet, it goes up, but it takes the portions that are really loud and it makes them, you know, doesn't amplify them as much. So you end up with a signal that looks somewhat like this. So if you look at the power of this signal here, it's always the same power, right? So the dynamic range of the signal is being compressed. I might go on a little bit on a tangent, but if you now, for those of you guys who are into music, when you look at load your MP3 in MATLAB, right, and pick two generations of musicians. Pick somebody from today, like you can even take the same band. Let's say you take Metallica and take their last album and take their first album. What you will exactly observe this.
That's
will-
different.
what we do in today's music, and what they do, when they mix the music today, they have a heavy compression on it.
Right.
And what that does, it makes it loud all the time, right? It's not only that it's loud by volume, it is loud that it never goes quiet, because even the quiet portions are amplified. And what that does, it makes it sound better, you know,
Well.
but it also makes you tired of it much sooner.
That sounds like
Wait.
equalizing it.
No.
No, it's different than
But wait, this is my issue whenever you use the compressor. Whenever you have the signals like that, it will like you have a noise in there. Because compressor
Because you
usually
have
will
a,
have a
because
noise.
you have a compressor, you know, if you have a noise here, you know, because let's say you stop playing, then there is some noise, you know, in the system. The compressor is not smart to realize it's a noise, and then it will amplify the noise too. So a lot of compressors, they come with a gate threshold that allows you to say something. If the signal is below this threshold, then gate it out. Don't let it, you know. But we're going into now guitar tricks, right? So let's, but that's why it's called compression, because it compresses the dynamic range of the power of your signal, right? No, it does that by expanding on the low end and compressing on the high end, right? So it's always in the middle.
So when you say low, we're not talking frequency, we're talking purely
We're
voltage.
talking magnitude. We're in the magnitude, right? We're frequency. Remember I talked about our view of the random processes, magnitude domain, time domain. We're not touching time domain right now. We're living in magnitude. We're looking at the random variable that is the amplitude of your signal, right? This has nothing to do with any frequency content of your signal at all. Right?
But I have another question. Why we have like, you know, a maze like that whenever we have the graph of uniform of the graph? We have a maze to the compressor and then.
Why do we want to achieve this? Why
No,
do
I
we want
mean,
this?
the left one. The left one.
This one?
No, left.
This?
The first graph, the first. Yeah, well, why we need like, you know, to plot is this one, and you have the expander over there. Why?
Well, to show you. How to show you? I mean, how am I going to show you?
I don't understand how does it work. I mean, like,
How does it work? The signal comes in here. Then, you know, they actually, I see what you're saying. This is a signal, right? And then what comes, there is your compressor here that looks somewhat like this, right? And then there is your A to D. And then there's all sorts of things, right? And then at the end, there is D to A. And then there is your expander. Right, that is, you know, and then there is yours. Right. So the trick is that these two cancel each other. They exist there only to adjust the statistical properties of the signal to the uniform quantizer. These two together are non-uniform quantizer. Right? These two are non-uniform quantizer, and then these two in parallel, in series, actually perform digital to analog conversion when you quantize with non-uniform quantizer. So although I have them as a separate blocks and separate functions, they actually together perform a function of a non-uniform quantizer. Okay? All right. So let's do some math. What I'm gonna that's the door. So what is our goal in over next couple of boards? Our goal is to determine the signal to quantization noise ratio formula, right? Just like the one we had the last time, but now in this particular scenario. So we're going to do step by step. So consider interval between two quantization, this interval between xi and xi plus 1. So these are two boundaries of the quantization interval. Here, from here to here, is one quantization interval. Anything that falls within this interval would be given the value xqi, right? And this interval, as you know, it grows, right? It starts being small and then it grows as the I becomes larger. What is the probability of what is the average quantization error in this interval? Well, quantization error is whatever is the actual value of x minus yi minus this value, right? Because you're going to ultimately represent this, whatever falls within this interval is going to be represented with this value, yi, right? Because anything that falls in this interval will be quantized as xqi, and xqi gets mapped into yi. So your quantization error is this. This is the power of that quantization error. Probability that you're going to fall within this interval. X goes from xi to xi plus 1. So this is a power of quantization error in the I interval, right? It's the expected value of this function. Expected value of this function is the function itself times the PDF of x dx evaluated in these boundaries, where this yi is equal to f minus 1 of x cubed I. Right? So that's the power of the quantization error when your input signal falls within this interval. And the width of the quantization interval delta I is given as xi plus 1 minus xi, right? And we know that this guy grows. But for small quantization steps, I can introduce some simplifying assumptions. Small quantization steps. Here are some simplifying assumptions. First one, I'm going to say that this yi is approximately 1/2 xi plus xi plus 1. All right? So I know it's not because this is curved, but locally, if these steps are small, then I can approximate this with a straight line, and I can approximate this straight line, and then if that's the case, then this ends up in the middle of the interval between xi and xi plus 1, and that's true for small steps. So if I do that, then I can say my xi is going to be yi minus 1/2 delta I, and xi plus 1 is equal to yi plus 1/2 delta I. So this is the first simplification that I'm going to introduce. And then the second one is the same simplification I introduced last time. I'm going to say that the PDF of x is approximately PDF of yi for x in the interval xi plus 1. In other words, I'm going to say if this interval is small enough, then the change of the PDF of the signal over this interval is relatively small, so I can assume that it's constant and it's equal to whatever is the PDF of yi. So now, armed with these two assumptions, I can now simplify this. Based on 1 and 2, this star simplifies as PQI approximately interval from xi to xi plus 1. But then I have this x minus xi, yi squared. And then PDF of x in this interval, I can approximate that this is PDF of yi, and then times dx. Now this PDF of yi is a constant, so this can go outside of the interval, and this becomes equal to PDF of yi, and then this is equal to x minus yi cubed over 3. Evaluated, xi is equal to yi minus 1/2 delta I, and then xi plus 1 is equal to yi plus 1/2 delta I, as a consequence of our first assumption here, right? This PDF I can go out as a consequence of the second, and then instead of xi and xi plus 1, I'm going to write these two equations for the bound. Now this becomes easy to evaluate. This is PDF of yi. When I substitute the top boundary, you see that this is yi plus 1/2 delta I. So yi and this yi would cancel. So you have 1/2 delta I cubed, which is 1/8 times delta I cubed, right? So I have 1/8 times delta I cubed. And then the same thing happens here, but yi and yi would cancel, and this minus here would make it plus again. So I have plus 1/8 of delta I cubed divided by 3. And now this is delta I cubed and delta I cubed, so this is 1/4 delta I cubed divided by 3. So it gives us our good old friend 1/12 delta I cubed times PDF of yi. So that's the quantization error in coming from the signal falling into the ith interval. And what is pleasing is that you get this delta I cubed again, just like in the uniform case. So that gives us a good feeling about what we did last time. Now let me continue, and I'm going to for a moment leave these two here. So use this part of the board. So if we continue now, from the, I guess, figure here, we have u is equal to f of x, just a general relationship of this compressor here. So if I take the derivatives of both sides, du is f of x prime times dx, right? So that's the mapping that associated with this compressor here. So I think u is essentially, this is u. Right? So u is equal to f of x, and this is x. So now if I expand this a little bit, then you end up with delta u approximately f prime of x, or I should say delta u I is f prime of yi times delta xi. Now, what is this? This here is your delta xi. So the quantization interval on the x-axis. This here is delta ui. And I'm saying that f prime of is the slope of this curve here, evaluated essentially at the point. So this is f prime evaluated at yi. Because remember, yi, we assume it's the middle of this interval, right? So I'm saying this interval here gets mapped into this interval. And because of this slope being larger for the lower, smaller, then smaller intervals on x get mapped into larger intervals here, and then slope being small here, meaning that the large intervals in this portion map into all uniform intervals across this ux. Now, so that's from the from the compressor itself. On the other hand, we have that delta U is equal, and I say delta UI, but that's the same as delta U, because delta U is the same. It's a uniform quantizer, so you know all of these intervals are the same. So delta U is equal to the total range of values divided by Q, which is 2 times U max divided by Q. U max is you know, the range of the quantizer. What is the input range of the quantizer in the uniform quantizer? So from here, you can say that your delta xi is going to be equal to delta U divided by f prime of yi, which I can say is equal to 1 over f prime of yi times u over q. Q, of course, is number of quantization levels. Okay? So that's delta xi. Why am I concerned about that? Because I need that here, right? So, which is the same, this is the same as delta I. So now, going back to our previous expression there, I get that the PQI, which is the power of the quantization error in the ith interval, is going to be this 1/12. Delta I is essentially this, right? Delta I. So I'm going to have let me actually rewrite this over there. So it's going to be PDF of yi times delta I cubed. And then I'm going to say, well, this is equal to 1/12 PDF of yi times delta I and times delta I squared. Now, instead of delta I squared, I'm going to substitute that in here. So this ends up being 1/12. And then this whole quantity squared. So this becomes u over q squared times PDF of yi times delta I divided by f prime evaluated of yi quantity squared. Where is this f prime coming? Because I'm squaring it from here. So there's u over q squared divided by f prime of yi squared, and then this is what is left from the previous line. So that's the quantization error in the ith interval. How do I get the total quantization error? I'm going to sum what happens across all intervals. So let me just get the total quantization error. So the total power of quantization error or power of the quantization noise is given like this. PQ is equal to sum 0 to q minus 1 across all different quantization intervals of PQI, where this is the power in the individual quantization interval. So this becomes 1/12, and then I have u over q squared. That does not depend, this is kind of constant that sits outside. And then I have sum, when I goes from 0 to q minus 1, of PDF of yi times delta xi divided by f prime evaluated at f at yi quantity squared. Now, this sum is consequence of us having a discrete number of quantization intervals. If that number is relatively large and our quantization intervals are relatively small, then I can squint a little bit, and what happens, this sum turns into what? Turns into integral, right? Because, you know, for small increments, when I'm summing, I'm actually doing integration. So if Q is large, which is usually the case, then this power of the quantization error becomes 1 over 12 u over q quantity squared integral, and then all of these guys become continuous variables. So this is PDF of x dx, and then here f prime of x quantity squared. And integrating from x min to x max, where x min and x max are a range of inputs, right? Assuming that they all fit in the range of the quantizer. So this here is a general expression, right? This is what we are after. So this tells us the power of the quantization noise in a system that has a PDF and then also has the compressor before you actually do the quantization. We did this last time, and what happened last time? Last time our compressor was input equal to output, right? Trivial compressor. If you say, how do I eliminate this compressor? But well, make f of x equal to x, right? So whatever is then presented here goes straight to the quantizer. And you can see if f of x is equal to x, then this x prime here becomes 1. So this becomes 1. And then what is this? Area under the curve of the PDF? 1. So here's our 1 over 2 delta 1 over 12 delta squared. So this kind of is a general expression that is valid for a uniform quantizer on its own, right? Because this part here all turns into 1, right? First, f of x is equal to x, so its derivative is 1. And then integral under the PDF is equal to 1, so this whole term here becomes equal to 1 in the case of the uniform quantizer. So that's the power of the quantization error. So the next thing that we need to remember is that power of the signal is equal to integral of, I guess I'm going to say x min to x max of x squared times PDF of x dx, right? So that's our power of the quantization of the signal. And then in this case, we get signal to quantization noise ratio is going to be 10 log of the power of the signal over power of the quantization noise, right? So this gives us all the tools that we require to be able to evaluate the signal to quantization noise ratio. Now, let's look at some practical applications of it. This is the end of the theory. We solved the problem that we were set to solve. And this is the problem of determining the signal to quantization noise ratio in the case where you have a non-uniform quantizer. A non-uniform quantizer, we split this into two parts: uniform quantizer and compressor, expander, and then this is the power of the quantization noise, and this is the power of the signal to quantization. This is the power of the signal, so this is the signal to quantization noise ratio. So let's take a look at a couple of case studies. Let's see how, just play with this result and see if we can get some practical insight in how this is used. So, the first case study that I'm going to look at is nonlinear quantization in, I guess, landline PCA. This is how we quantize, sample and quantize voice signal in our landline telephony. What we use in a landline telephony, we use something that's called mu compression. And in this case, your compressor has the following function. It is ln of 1 plus mu magnitude of x divided by ln 1 plus mu times sine of x. So that's the transfer function of the mu compressor. If memory serves me right, mu is equal to 255 for the landline telephony. So if you were to plot this, this is how this compressor looks like. So it assumes that x is between -1 and 1. In other words, the signal is normalized so it doesn't overdrive the compressor here. So this is how this compressor look like. If you look at this, when x is very large, when x is equal to 1, it's actually ln of 1 plus mu over ln of 1 plus mu, so it's equal to 1. And then, kind of if you draw it, this is how it looks like. It's quite steep, you know, this compression. So you may want to try it in MATLAB. You can see as mu increases, you're kind of pushing this curve more and more towards the axis. For mu equal to infinity, then you end up with a step function. Right? But that's not where you want to go. So the mu here actually is a parameter that allows you different levels of compression. For mu equal to 0, you should actually, for mu equal to 0, there is no compression, right? F of x is equal to nothing. What am I? You just plot this for different mu, right? My impression, let me see, if mu is equal to 0, then this becomes 0 over 0. So as mu becomes smaller, then this becomes kind of more and more of a straight line. Now, mu compression we use.
Is that absolute value of x or?
Absolute value of x here. Absolute value.
That's multiplication.
Yeah, times. And this is sine of x, right? Signal function. If x is positive, it's 1. If x is negative, it's -1. Very good. Now, we use mu compression is used in US, Canada, Japan. There's an alternative compression method that's called A compression, which is very similar. I have it here also. Fa of x is equal to now 1 plus ln A times magnitude of x divided by 1 plus ln of A. And then also it's true for x between -1 and 1. And I forget what was the actual value of A. But if you plot these two, they're almost identical. So I don't know what was the reason for inventing yet another compression. It says here, I have a note, A produces slightly larger dynamic range at the expense of the signal-to-noise ratio for small signals. So A compression is slightly smaller than a mu compression. By convention in international calls, A law is used if at least one country uses it. Right? I have the notes here. So if you call from here and you call France, then your communication equipment is smart enough to use A compression. So because on the other end, it's going to be decompressed using A. Okay. Now let's work with this expression here and kind of derive the signal-to-noise ratio for this particular case. If I look at this mu here, then what I need is f prime of it. So f prime mu of x is going to be equal to mu over 1 plus magnitude like this times ln 1 plus mu. So that's the derivative of this compression function here. We need it for this one. So if we substitute, we get that the quantization power of the quantization noise is going to be 1/12 delta squared, because U over Q is nothing but the delta of your uniform quantizer. And then you have integral from -1 to +1. Now PDF of x. So let me just put this in here. So this becomes 1 plus mu magnitude x squared ln squared of 1 plus mu divided by mu squared times PDF of x dx. And if you take out everything that's a constant, so you end up with 1/12 delta squared, and then ln squared 1 plus mu over mu squared. And then you have an integral from -1 to +1, 1 plus mu x squared, sorry, the whole thing squared, times PDF of x dx. Okay? So, so that's how these, the power of the quantization noise look like. Now, this mu is an adjustable thing. It helps you, decide how your compression looks like, how much of a compression you have. And let me just, it's not in the notes, but let me just sketch what we are actually accomplishing here. If your PDF is, let's say, spiky like this, right? Then what you would like to have is relatively large mu. And then what that does, it actually does this. So that the product of the two, it takes these values here and makes them smaller. Therefore, the value of this integral becomes small. So by varying mu, you can actually vary the amount of the compression. And the spikier your distribution is, the larger mu you want to have. Right? And this 255 that we use for voice tells you that the voice is very spiky when it comes to PDF. And I would like you to verify that. You know, you all have access to MATLAB. Some of your laptops are able to record the sound. So say something or get some voice, read it into MATLAB, and generate a histogram of it. And what you will end up having is something like really spiky, because a lot of samples are going to be very close to the origin. And therefore, this mu of 255 tells you that it's a relatively high compression that is used in the voice. So this term is 1 mu times 2x squared, and this here is PDF of x. And by multiplying these two, you're actually trying to minimize this part of the quantization noise. This is the part that is subject to optimization. This other part is constant, right? It does not depend on just a bunch of constants that depend on the quantization steps of quantizer. Go ahead.
What is mu by definition?
Just a parameter. Mu is a parameter. Yeah, for different values of mu, you get different levels of compression, right? So in general, I mean, this is the form of a compressor, and this essentially gives you infinitely number of different compressions, right? But so then by choosing different mu, you actually vary the compression. Therefore, we got one law, which is this mu law, that allows me to cater to large classes of the signals by just changing mu. You can say if the signal happens to be voice, use mu equal to 55. If it happens to be some other signal that is not as peaky as voice, then use mu 15 or mu, whatever is the range of mu. As a matter of fact, through the next example, I'm going to show you how you choose mu, right, for a given signal. Right? But this is one law that gives you a family of curves that you can adjust now to the properties to your signal. Right? So if you implement this in code of some sort, then somewhere in the code there is a mu, and then by changing this mu, you end up, you know, that's one parameter that allows you to compress all sorts of different signals. Okay, let me now help you kind of discuss how you choose different mu. I have two examples here. The first one is kind of messy, so let me skip the first one, and I'll just go to the second one, and then if there's a time at the end, we'll go to the second one. So let me look at this case. This is case 2. Let's say I'm compressing Gaussian signal. I'm quantizing Gaussian signal. So the PDF of x is approximately, let me see, something like this: k e to the minus x squared over 2 sigma squared for x smaller than 1, 3, and 0 otherwise. And this case is such that it makes the PDF work. The area under the curve needs to be equal to 1. So my signal is essentially looking like this. It is bell curve centered at the origin, and this is my, let's say, 1/3, 1 over 3 minus 1 over 3. So that's how my signal looks like. It is in this interval between minus 1 over 3, and it has this Gaussian shape of the PDF. So this is a PDF of x. And the question is very practical. You know, I want to quantize this signal. What is the best mu that would work for this signal? How do I select the mu? And the way how you work with that is you look at the power of the quantization noise. And this is going to be based on this general expression here. It's going to be 1/12 delta squared ln squared 1 plus mu over mu squared. And this is minus 1 over minus 1 to 1, 1 plus mu x squared times k e to the minus x squared over 2 sigma squared dx. And I hope, you know, this is not giving me so. And I assume here that the sigma is equal to 1. So that's how this guy looks like. So now how do you do that? Well, if you look at this whole expression, you would say PQ is equal to K, that doesn't change, over 12, delta squared, and then times f of mu, where mu, f of mu, is going to be this whole thing, ln squared of 1 plus mu over mu squared, integral from minus 1 to 1, 1 plus mu x times e to the, actually between minus 1, 3 and 1, 3, right? Because this guy does not extend outside of 1, 3. Sorry, I forgot, you know, it's limited, you know, in this range. And minus x squared over 2 dx, because sigma is equal to 1. Now, this is obviously a little, there's square somewhere here, right? This is a relatively complex integral. It cannot be solved analytically, but it's very easy to solve this numerically. And if you do that, here's what you end up. Mu, and here's f of mu. And you can vary mu. 0, 1, 2, 3, 4, 5, 6, and so on. So this is 1, 0 0.7, 0 0.6, 2, 0 0.59, then for 4, 0 0.58, then for 5, 0 0.59, and then for 6, 0 0.59, and then for 7, 0 0.6, and so on. So if you plot, here's what you get. You end up here with mu, and this is your f of mu. And f of mu will have this kind of behavior where it bottoms for mu equal to 4, around 4. So that's practically how you would determine this. You're actually searching for mu that minimizes this integral here. And depending on what you plug in terms of the PDF, you end up with the different mu's that you would use for this signal. So if you know the statistical properties of your signal, then through this kind of evaluations, you can choose what the appropriate mu is for that signal. We did the same kind of evaluations on the voice signal, and we determined that the mu value for which the quantization error for voice is minimized is actually 255. So because voice is, as I said, very spiky, it has a very, very hard, high probability density function around the origin. It has what we call a Laplacian distribution. It is exponential distribution, symmetric about the origin. So that's how you would choose mu. Now, an interesting thing to look at is last time we looked at the uniform signal through uniform quantizer. If the uniform signal is passed through a uniform quantizer, what is the quantization noise error? We had it as 112 delta squared, right? And that was the case. Now the question here is, what is the quantization, signal to quantization noise ratio if I take my uniform signal and pass it through a system that has non-uniform quantization? In other words, we looked at the last time and we said, well, if I take a uniform signal and I pass it through a uniform quantizer, signal to quantization noise ratio was 20 times log of Q, where Q was the number of quantization levels. Now, if we have a uniform signal and we pass it through a non-uniform quantizer, you expect that there will be some penalty. Just like we had a penalty associated with Gaussian signal from non-uniform quantizer, right? So let's, as an exercise, evaluate that as well. And this is going to be the second case. I'm going to leave this result here. So this is a case, I guess case 1 now. We have a PDF now of x equal to 1/2 when x is between -1 and 1 and 0 otherwise. So we have a signal that has PDF looking like this. This is x, PDF of x. The signal is existing between -1 and 1 and has a uniform probability density function. So the quantization noise in this case, PQ, becomes 1/12 delta squared ln 1 plus mu squared over mu squared, integral of -1 to +1, 1 plus mu x squared times 1/2 dx. So that's the power of the quantization noise. Now this integral can be evaluated relatively easy. So this is 1/12 delta squared ln squared 1 plus mu over mu squared. And this is even function. You see that this is an even function of x. So I can say that this is 2 times integral from 0 to 1, 1 plus mu x, and then I can put this 1/2 outside to cancel. And then instead of dx, I can write this d of 1 plus mu x, and I can divide by u to make everything balance. There's a square. Do you see that this is true? Because what is d of this? It's mu dx, right? And mu cancel, so it's just dx, right? But now I have t squared dt, right? So this becomes 1/12 delta squared ln squared 1 plus mu over mu squared. And then this is 1 plus mu x to the power of 3 over 3 mu between 0 and 1. So the power of quantization noise in this case becomes delta squared over 12. Then I have again this constant here, which is ln squared 1 plus mu divided by mu squared. And then when I substitute 1 here for x, I get 1 plus mu cubed over 3 mu. Actually, let me just do 1 plus mu cubed over 3 mu. And minus, when I substitute 0 here, then I just get 1 over 3 mu. Right, so that's one way of expressing this. Let me see what I did in this here. I brought mu squared inside, and then this becomes delta squared over 12. And then I have ln squared of 1 plus mu, everything over 3. And then I have 1 plus 1 over mu q minus 1 over mu q. And that's how I have it written in notes, which is essentially the same thing. So that's the power of the quantization error. Now, if you look at now your signal power, it's 1/12 of 2u0 cubed. Actually, let me just get to that point. So this becomes an integral from -1 to 1 x squared times PDF of x dx, right? This is how we calculate the signal power. So this becomes integral from -1 to +1 x squared times 1/2 dx, because the PDF is equal to 1/2. So this is equal to 1/2 x cubed over 3 between -1 and +1. And this is, let's say, I have here 1/6. When I substitute 1, so this is 1. When I substitute -1, this is -1, so plus 1. So I get 1/3. So that's the power of my signal. And so that's as far as power of the signal is, but I want to actually express, so this is not the best way of doing this. So let me just see what I did here. I say, well, your range here, which is 2, is equal to q times delta. So this whole 1 here is q times delta over 2 squared. So I guess I can write this PS. In general, for uniformly distributed signal is 1/12 times 2 times u0 squared, where u0 is the maximum. In this case, u0 is equal to 1. That's the maximum range. But u0 is equal to 2 times u0 is equal to q over delta, q times delta, so this is equal to q times delta squared over 12. In other words, this is equal to q squared delta squared over 12. And now I can form the signal to quantization noise ratio in this case. So SQNR in this case ends up being 10 log of power of the signal divided by power of the quantization, which is 10 log. Power of the signal is q squared delta squared over 12. Power of the noise is going to be delta squared over 12 times ln squared 1 plus mu divided by 3. And then there's this term here, 1 plus 1 over mu cubed minus 1 over mu cubed. Okay? And then you see the delta squared over 12 and delta squared over 12 cancels. So we end up with 10 log of q squared, which is 20 log of q. And then minus this 10 log of ln squared 1 plus mu over 3 1 plus 1 over mu cubed minus 1 over mu cubed close. And the whole point of this exercise is this. You recognize the terms here. Signal to quantization noise ratio for uniform signal is 20 log of Q. This is our good old friend. This is what it was when your quantizer was uniform, right? Now, because the quantizer is not uniform now, you have this term here, which is the penalty that you're paying for your signal not being adjusted to the quantizer. And you can test this term here, but you will see that for mu, larger mu, the larger the mu is, the larger the penalty is. Because you can see, as mu becomes larger and larger, then this whole term here becomes equal to 1. And then this grows as a ln squared of 1 plus mu. So for the increasing mu, this term grows, and therefore your penalty becomes larger. When mu goes to 0, then this becomes the subintegral. This not subintegral. This term here becomes close to 1, and as this term becomes close to 1, then log of that becomes equal to 0. So for mu equal to 0, we're back to our uniform quantizer, and this term vanishes. So this is just yet another exercise that shows you how you deal with these kind of things, you know. And in practice, you're always going to be dealing with a uniform quantizer, and then you're going to a lot of times have circuitry up front that performs the compression, and this allows you to understand what kind of compression you need to apply and what are the penalties in your signal to quantization noise ratio if you know the PDF of your signal and the amount of compression. And the idea here is that by choosing a proper compression, you can probably gain in a signal to quantization noise ratio. Now, you can trade that gain for the bandwidth, because if this is larger than what you need to provide for a given signal, then you can actually operate on Q and get a smaller number of bits that you need for a given quantizer. This is why when you calculate, like if you don't do any compression, and if you try to quantize noise, the number of bits that you need is I believe, 10 or 12. And then when you use this compression, you can go back to 8 bits and still get a sufficient quality of the signal, so that it's imperceivable to us that it has been quantized and reconstructed back. Okay? Any questions? All right, so that's the end of the quantization. Next time we're going to try start talking about PCM and how you turn these quantized levels into bits that we're going to be transmitting over the communication system.
What is the first midterm?
Yes.
That's a good question.
Any homework on that?